Hi everyone, welcome to this new episode of Astronomy on Tap London, as usual, stay at home edition. Thank you for joining us today. I'm hosting the event as usual with Corentin. Hi Corentin.
Hello.
Well, I hope your sight is very sharp, and if not, wear your glasses as Corentin and I have done, as you can see, because we are going to look at a very detailed view of a galaxy far away from us. Before introducing our guests, I would like to remind you that we'll have a Q&A session after the talk, so please post your questions in the YouTube chat. And also don't forget to subscribe to our YouTube channel and to follow us on our social media to keep up to date with the next events. So I see also a very nice pattern in terms of hair, curly hair today, but we can ensure that we don't choose our speakers because of their hair. So our guest today is Dr. Francesca Rizzo, that is also known as Franci, and indeed I'll call you Franci today because it will be very difficult for me to call you Francesca. So Franci is a researcher at the Cosmic Dawn Center in Copenhagen. Hi Francesca, and thank you for being with us today.
Hi.
So Franci is going to talk about a very special galaxy for a few reasons that we'll discover in a few minutes. And this galaxy appeared in a paper on Nature last summer, so a very important publication. And the galaxy was featured in several press releases when the paper was published. And so one may expect that being this a special galaxy, you were following it since a long time and working a lot on it. But however, the way you ended up analyzing this galaxy is quite curious, Franci. So we want to know more about it.
Yeah, so I started to work on this galaxy just because during the second year of my PhD, I wanted to apply the software that I had developed to real data. But then what happened was this. So for 4 times, I had the opportunity to observe the target that I want to observe, but there was a thunderstorm the first time, the second time. And then in the end, I had to finish my PhD. I had to write other two papers, and then decided to look into an archive containing data taken from other people. And I decided to start working on this galaxy just because I like this galaxy. So I didn't know, I didn't expect anything. It was just by chance.
Right. So in some cases, like thunderstorms are not that bad because then you end up on very special targets. Okay. Thank you, Franci, for this tale. So, and now let's move on. And as you know, we post quizzes and little games on our social media before the live event. And Corentin is going to summarize this week's questions for you. During the talk, feel free to post your guess to these questions in the chat, and we'll give the answer right after Franci's talk. So, Corentin, the screen is yours.
All right, so this week we posted two pictures and questions together on our social media. So if you're not following us on Facebook or on Twitter or on Instagram, do it now. So the first question was this picture here, and the question is what is the ring in this picture? The first answer possible is the Eye of Sauron, or it's a lensed galaxy, or it's an electric hot plate, a planetary nebula, or an interspatial portal. So if you don't know the answer, you can also post your favorite answer, and we'll discuss the correct one, unfortunately, at the end of the presentation. So you can write, you can post your answer just down there on the chat. We had a second row of questions, which is about what is a gravitational lens. So is it a giant telescope, Is it a lens that measures the gravitational force? Is it a distribution of matter that bends the light from a distant source? Or is it something predicted by Albert Einstein? So same here, post your answer in the chat and we'll discuss all of that at the end of the session.
Thank you, Corentin. Okay, so now, Franci, the screen is yours and start whenever you're ready.
Thank you. Okay. Can you see my screen?
Yes, but we can also see some dark areas.
Oh, okay, I try again. Now?
It works now, yes.
Okay, thank you very much. Okay, good afternoon, good evening, everybody. During this presentation, we will discover together what is this nice ring that you can see here. But before describing what is this ring, I want to tell you something about galaxies. So as you may know, during this presentation, I will talk about galaxies, but we live in a galaxy that is called the Milky Way, and you can see here a very nice picture of the Milky Way. And you can see that in the Milky Way, there are a lot of stars. So there are billions and billions of stars that are these white points here. But there is also the dust, that is this dark region patches that you can see in this picture. So in general, all galaxies, both the Milky Way and the billions and billions of stars, of galaxies in the universe, are made of these four ingredients. So there are the stars, there is the dust, there is the gas, which is one of the main ingredients of the galaxy, because the gas is what makes a galaxy alive. This is because new stars can form only from the collapse of the gas, which is mainly hydrogen. And then there is the dark matter. So the dark matter is the predominant source of gravity within a galaxy, and is called in this way because of two reasons. The first one is because the dark matter is not able to emit any light, any radiation, so it's dark. And then the other reason is because in astronomy we call dark every object for which we don't know the nature. And in the case of dark matter, we don't know, unfortunately, which are the nature of dark matter particles. Now, during the presentation, I will also talk about very, very distant galaxies. And in astronomy, the distance is a synonymous of age. This is because the light travels in a finite amount of time. So if you look at a distant galaxy, it means that you look at a galaxy when the universe was very young. So in other words, the universe now is 13.8 billion years old, meaning that in the Milky Way, such as in other nearby galaxies, there are stars that are as old as the universe. So there are stars that are 13.8 billion years old. On the other hand, when you look at the sky, you can see not only nearby galaxies, but you see also distant galaxies. And distant galaxies are galaxies in which there are stars that are 6 to 2 billion years old. So these galaxies are considered, as you can see here, since these have intermediate age, these are considered the teenager galaxies in the universe. However, the main focus of my research are the very, very distant galaxies. So in my research, I studied the galaxies that are typically younger than 2 billion years old. So these are the baby galaxies that live in our universe. Now, similar to what happens to humans, also in the case of galaxies, there is an evolution of their physical properties. So just to give you an example, we know that distant galaxies have sizes which are much smaller than sizes in the nearby galaxies. And in general, when we study the galaxies, we study the evolution of their properties, because by studying the evolution of the properties of galaxies, we can learn something about the history of the universe, and also we can learn something about the history of the Milky Way. Now, we know very well, because astronomers in the 70s and 80s started to study both the Milky Way and nearby galaxies. So we know very well that the gas within nearby galaxies moved in a well-ordered way. So there is a regular rotation both in the Milky Way and in nearby galaxies. However, the motion of the gas within distant galaxies is a matter of debate. So in particular, there are current galaxy formation models that say that the motion of gas within distant galaxy is very different with respect to the motions of gas in nearby galaxies. This is because in distant galaxies, there are a lot of mergers, accretion, interaction of galaxies, accretion of gas from the surrounding to the main body of the galaxies, and also supernova explosions. All these events led to very turbulent, chaotic motions within distant galaxies. However, the problem is that the observations of the motions within galaxies and the observation of the motions within distant galaxies is very challenging. So the main goal of my research is to test these galaxy formation models and to try to understand how the gas moves within distant galaxies, so that we can learn which were the physical phenomena that shape the galaxies in the distant universe. Now you are wondering, how can you measure the motions of gas within galaxies? And the answer is the Doppler effect. I think that you are all familiar with the Doppler effect. And one of the most famous examples of the Doppler effect is the motion of the ambulance with a siren. So every time that there is an ambulance that is approaching us and is moving away from us, what happens is that there is a change in the pitch, in the note of the sound wave. And in particular, there is an increase of the pitch when, of the note when the ambulance is approaching us, and a decrease when the ambulance is moving away from us. Now, the problem is that, of course, we cannot hear the sound coming from the galaxies. So one way to measure the motions of gas within galaxies is to use the Doppler effect, but not on the sound wave, but on the light, because the light is made up of waves. So the other point is that of course, to measure the motion, we have to measure something that is moving. So I want to just give you an example of what happens in the case in which the galaxy is not the motion. So the galaxy is not moving, so the galaxy is at rest. So let's assume that the galaxy emits light at a specific color. And let's assume that this color is the yellow one. So if the galaxy is at rest, what we can do is to observe this yellow color, as you can see here. So by observing this galaxy, I observe that this is yellow. However, in the case in which there is a motion within a galaxy and I measure the light coming from this region here of the galaxy, so region A, that is the region in which, as you can see from the arrow, the gas is moving towards the observer. So in this case, what I measure is not the yellow light, but is a color that is shifted towards blue color. So as you can see here, depending on the specific velocity of the gas within this region, I will measure the emission of the galaxy with a color between the yellow and the blue here. On the other hand, if I observe the region B, so the emission from this part of the galaxy in which the gas is moving away from the observer, the color in this case will be shifted towards red color. So again, depending on the specific velocity of the gas within this region, I will have something between the yellow and the red color here. So in other words, if you observe a galaxy and you see that there is a shift with respect to the expected color, in this case, as I said before, I expected that this galaxy emitted yellow color, then it means that there is a motion within this galaxy. Now, the other issue, as I told you before, is that we have to observe the motions within galaxies, but we have to observe the motions within distant galaxies. Now, again, just to give you an idea, the observations of distant galaxies is similar to what is happening here in this picture on the right-hand side. So here you can see a picture of a huge room in the Louvre Museum, and you see that there are a lot of people here, and you can barely see that here there is a painting. But we cannot see which is the subject of the painting. We can barely distinguish the color there, even if we take this picture with a new generation smartphone. However, if we are very close to the painting and we take a picture with an old smartphone, we can see the detail of all the details of the painting. We can see very well the subject. We can see the background of the subject. So the observations of distant galaxy is similar to these two images here. This is because when we observe a nearby galaxy with a new generation telescope, we can see that all the details of this galaxy. So we can see that it has two spiral arms. This is one of the closest galaxy to the Milky Way. And for example, we can measure very well the size of this galaxy. However, if we observe a distant galaxy, also with a new generation telescope, what we see is something like this. So it's a blob in which you cannot distinguish whether, for example, there are the spiral arms or not. You cannot measure the size, for example, of this galaxy. So the observations of distant galaxy is very challenging. Now, one of the way to, let's say, partially solve this issue is to observe galaxy by using a gravitational lensing. What is gravitational lensing? So if you have a distant, a massive object, what happens is that it causes a warp in the space-time, as you can see here. So the light from a distant object without this warping is undistorted, so it's very straight. However, in the presence of a warp, so in the presence of a massive object, what happens is that there is a bending in the path of the light. In other words, this effect is similar to what we have in the case of a magnifying glass. So when there is a magnifying glass and there is a light bulb behind this magnifying glass, what happens is that there is a bend in the path of the light, so that in the end, the light bulb seems bigger. So this effect is called gravitational lensing, and it can be used to observe distant galaxies in very great details. So here there is an example in which the distant galaxies, these red points here, and as you can see, when the light from this distant galaxy are closer to the massive nearby object that is called the lens, what happens is that there is a bending of this light, so that in the end, if you observe with the telescope this distant galaxy, what you see is a virtual image of the distant object. So you see a distorted image of the distant galaxy that is this ring here. Now, here I put some picture of very nice and famous gravitational lenses. And in all three cases, the yellow light that you can see here is the nearby massive object, that is the lens. And this ring, the blue ring are the distorted image of the distant galaxies. Now, in my study, what I did was to combine gravitational lensing and ALMA. ALMA is a telescope, so the name is the acronym for Atacama Large Millimeter Array, and is located in the Atacama Desert in Chile. Actually, ALMA is an interferometer, which is a combination of telescope that works together to simulate a giant telescope. In particular, in this case, they simulate a telescope with a size, a diameter of 16 kilometers. Why this is important? This is important because you need a very large size of the telescope to observe the details of the distant object, and in particular, in this specific case, you cannot build a telescope with a size of 16 kilometers. So what you do is to combine the effect of a small telescope, which are these telescope here, these are the radio antenna of ALMA, to have to simulate the giant telescope. So for my study, what I did, as I told you before, is to combine ALMA and gravitational lensing to observe this galaxy, which is called SPT0418-47, this phone number. And this is a very, very distant galaxy, and the light from this galaxy took 12 billion years to reach us, meaning that we are observing this galaxy when the universe was 1.4 billion years old. So this is a very baby galaxy. Here in these figures, so you can see in the top panel, you see the light from this galaxy that, since it is a gravitationally lensed galaxy, is a ring. And then on the bottom, you can see again the lensed galaxy, but the colors, I colored this galaxy this time with the blue and red to indicate the part of the galaxy which is approaching and receding us. Of course, to observe, to study this kind of galaxy and to learn something, we need to have information about the intrinsic shape, because as I said before, is the virtual image. So what you obtain if you are observing a magnifying glass, you have the virtual image that is the light bulb is bigger. So in this case, this is a virtual image, and so you need a software to study the intrinsic, to reconstruct the intrinsic shape of the galaxy. And this can be done if you know the mass of the lens, because by knowing the mass of the lens, you know which is the amount of bending caused by the lens, so that you can reconstruct the intrinsic shape. So in my study, what I did was to reconstruct first the intrinsic shape of this galaxy, and then I could measure the motions of the gas within this galaxy. So here you can see in the top panel the reconstructed distant galaxy. And you see that it is possible to measure the size of this galaxy, so it's not a blob. You can see all the details of this galaxy. In the bottom panel, you see again the color according to the approaching or receding side. And you see that there is a nice variation from red to blue that indicates that the motions of the gas within this galaxy are very regular. Now, what we learn from this study? We learn that despite this galaxy is a very distant galaxy in which that is forming stars, so in which there are a lot of supernova explosions, the motions within these galaxies are very regular, so there are no chaotic and turbulent motions. Of course, this challenge all current galaxy formation models, and it poses a lot of questions about how is it possible to have this regular motion within such a distant galaxy. And that's all. Thank you very much.
Thanks a lot, Franci. It was a great talk with a very special object. Okay, so before going to the questions, feel free to post them in the chat. Let's go back to the questions that we presented at the beginning. So, Corentin.
Yeah. Okay, so the first question was, what was the ring in the picture? So if you have followed Francesca's presentation, you know that it's a lens galaxy. Unfortunately, it's neither the Eye of Sauron or an interspatial portal. That would have been even slightly more exciting, even though this is already very, very much exciting. The second question is, what is a gravitational lens? Oh, I just see that someone is posting the answer. So what is a gravitational lens? A gravitational lens is not a lens that measures the gravitational force. That's a mistake by me. It's supposed to be number 3 and number 4. Oops. Nope. There, you didn't see the mistake. That's great. So it's something predicted by Albert Einstein, but it's also distribution of matter that bends the light from a distant source. Sorry for the mistake, or to catch the ones that were not following properly.
No problem. And so maybe something that Franci, you can comment on. So you showed your galaxy, which forms a perfect ring, but also some other type of lensed galaxies that have like partial rings or just arcs. So is there an improvement in the details that you can see in your perfect ring with respect to other kind of lensed galaxies?
Yeah, so it's very unusual to have the perfect ring, and this happens when you have a perfect alignment between the massive nearby galaxy and the distant galaxy. Of course, since you have this alignment, what you have is that the magnification is perfect in this case. So you can see that the distant object is very bright, and you can see with the best details the distant object.
So we have a comment on the chat saying that the gravitational lens could also be called actually a giant telescope, given the magnification. What's your opinion on that?
Well, well, it can be considered a telescope, but yeah, this is a gravitational lens by definition is a matter that bends light from the distant source. So in a way, it can be considered a natural telescope.
Yeah, indeed, it's a very convenient effect. I mean, you have a great view on galaxies for free, basically.
Yeah.
Yeah. So we got a question in the chat. Well, yeah, Franci, go on.
No. I want to say that, of course, it's very difficult also to pick these objects that are gravitational lens. So you have to look for this object, and then you have to look for the background object, because of course it's not always a galaxy, it can be something else.
Yeah. So Corentin, would you like to take the question from the chat?
Yeah, so we have a question from Tim Sheridan, who's asking about whether there are supermassive black holes at the center of early galaxies. And then there's a follow-up question is, how did they form?
So there are supermassive black holes at the center of distant galaxies, or at least it is expected that they are, because we can measure the effect of these supermassive black holes. However, for example, this is not the case for this specific galaxy, in which we cannot clearly see any effect from a supermassive black hole.
And how do they form in these galaxies?
Do you mean the supermassive black?
Supermassive black, I guess so, yeah.
Okay.
Correct me if I misunderstood your question, too. But
well, this is very interesting. The point is that we still don't know how supermassive black hole formed in a very distant galaxy. So there are a lot of possible scenarios. One is that there is an interaction between different stars. The other one is that there is concentration of gas in the inner region that led to the formation of a supermassive black hole. The other one is that there is a very giant star that then explode and go into a supermassive black hole. So a lot of scenario, but unfortunately we still don't know which is the one that led to the formation of supermassive black hole, or it can be that there are all three.
Yeah, the follow-up question here is how did they form so soon after the Big Bang? And I mean, somehow you covered that there is a seed black hole and it has to accrete quite a lot of matter in very short time. And this is something that we cannot still prove. And actually, the previous event 2 weeks ago was really covering this point. So Tim, I really suggest you to go and have a look, because it was very interesting. Okay, so let's move to the next question. from Ayush, so it's thanking you for the talk and asking how you actually first discovered this object. I mean, you covered it a little bit at the beginning, but maybe the question would be also why did you go on this object specifically?
Well, I have to say that this object was discovered for the first time because it was very luminous. So, and this is because there is gravitational lensing. So you have this magnification effect that allows you to see this very luminous object. But at that time, this object was observed with an old telescope. So this object, despite gravitational lensing, was a blob. Then with ALMA was observed again in another wavelength range. And I saw the first image of this object in another paper that focused on another topic. And so, yes, I started to work on it just because I liked that it was a perfect ring, and I knew that I can have a lot of information because of the magnification effect and because of the details with which you can study this distant object.
Okay, so we have another question. Corentin, would you like to take it from the chat?
Yeah, so we have a question from Johannes Stoiber. I'm sorry if I don't pronounce your name correctly. So the question is, how did you reconstruct the intrinsic state of the galaxy from the distorted image? And could you apply a similar procedure to reconstruct a lens galaxies that is not a perfect circle?
I developed a code during the first part of my PhD to reconstruct the shape of galaxies starting from these rings, and also from galaxies that are lensed but are not perfect rings, such as the one that I showed during the presentation. And how this can be done? This can be done because if you know the mass of the lens that is distorting the path of the light coming from the distant source. So in other words, if you know the amount of the distortion in the space-time, then you can go back and reconstruct the path of the light and go back to the intrinsic shape of the galaxy.
That must be a very interesting kind of analysis to do. And yeah, maybe one last point that we can cover. So this looks like a kind of special object, but you said that observing this kind of galaxies challenges our models of galaxy evolution. So what's your view? Do you expect these kind of galaxies to be common or at least more common than just, a few special objects? What do you think? What would you expect?
Well, actually, I extended this analysis to other 5 galaxies, and other collaborators extended this analysis to other 4. So now we have a sample of 10 galaxies in total that show this behavior in the motions of their gas. So basically, there is an increasing number of galaxies that seems to behave in this way. So very regular, no chaotic motion and no turbulence. So it seems that they are not so special.
So there is need for more data for sure. Okay, well, Corentin, we have another question.
Yeah, we have yet another follow-up question on this question about lensing. So you said that the background galaxy is distorted by the lens, and that is determined by the mass of the foreground object. How do you determine the mass of the lens?
This is one of the 3 parameters of the model, meaning that the only unknown of your model is the mass of the lens. So, and the mass of the lens can be guessed, let's say, by the size of the ring. So if you have a large ring, it means that the mass of the lens is very huge. Well, if you have a small ring, it means that the mass of the lens is very small. So it's the size of the ring that gives information about the amount of mass that is distorting the space-time.
Thank you, Francesca. I think Johannes got quite interested in gravitational lensing. Okay, so I don't see more questions in the chat. So thank you, Franci, very much for your talk. It was very interesting to hear about gravitational lensing. It was the first time in almost one year of events. Thanks a lot for being with us. Okay, and we have, in the meantime, we have a comment from Tim. We have fairly recently started to be able to measure gravitational waves. Yeah. Okay, so yeah, see you in 2 weeks. Take care. Bye, everyone.
Bye.
Before we leave, if you like this video, you can also go back to our previous ones and enjoy all the previous ones. We made like several over the last year, over the multiple lockdowns, so you can enjoy them. We had just 2 more questions.
Oh, right.
Yeah, sure.
Okay. Good. 3 more. Oh, okay.
Many questions coming.
Tim is asking whether you can use gravitational wave as lensing.
Well, gravitational wave as lensing is very difficult. You can use gravitational lensing to have much more information about the gravitational waves, because the gravitational waves are very, very weak signal. And so by using gravitational lensing, you magnify the signal from the gravitational waves. But in any case, the gravitational waves are an effect related, or we can say the same as gravitational lensing, because it's a warp of space-time in both cases.
Okay, and the next question from Jack. So do you think the Hubble classification is flawed? So maybe, like, given your discovery, do you think that this could affect the Hubble classification of galaxies?
Well, the point is that the Hubble classification is applied only to nearby galaxies. So in the very distant universe, so now we are talking about galaxies which are younger than 1-2 billion years old, we usually do not apply the Hubble classification, because we still are not able to observe the different morphology, because the Hubble classification is based on the morphology of galaxies. So it distinguishes the spiral with respect to an elliptical galaxies. But unfortunately, in the high redshift universe, we still don't have the instrument to observe the optical emission, which is coming from the stars, and we still do not apply the Hubble classification. So the Hubble classification is something that is valid only in the nearby universe.
Okay, so if there are no more questions, now I'm going to say goodbye and for being with us today.
Thank you very much, and thank you for the question.
Thank you.
Bye.